Okay, welcome everybody. This is Spring 2022 version of Applications of Parallel Computers, CS267. I want to thank our Vice Chancellor for Research, Kathy Yalek, who used to be an instructor on this class for the last, at least consecutively for the last 5 years and many more years before that, for a majority of these slides. And there's one unanswered question, which is what percentage of the undergrads in the waiting list are going to get in? I actually don't know. Right now, the official number is we're full. We have requested an increase, and what happens at the beginning of semester is every class requests these kind of things from a few staff that is supposed to handle all of these changes, and they get overwhelmed. So we're still hopeful this is going to happen very soon, but there's no guarantee. And because we're basically asking an exception and saying that because we're posting things online, we can go over the room limit. We are at the room limit, assuming there will be a room we'll ever gather. So let's start the actual lecture. So what's a parallel computer? The title of the course has parallel computing in it. It's if you go to a machine room in one of these supercomputing centers, such as NERSC, which is up at the hill, like I would say 50 feet from where I'm actually standing right now, is you're going to see all these cables that connect a huge machine together. And this is actually a real photo. You'll be always surprised with how many cables are in there. And that speaks a little bit about how important the interconnect between these machines are. But at the end of the day, it's really a machine with a lot of different components connected through an interconnect, and we'll see different variants of them. But why do we do that? It's really about to get high performance out of our whatever task we have. If the performance of our computing is not sufficient for our purposes, and then we go for really parallel computing. So let's give a simple example for this. Let's say you have lots of numbers, and you're going to do factorization of them. You might think about this. Okay, here's the simplest way I can handle this thing. Factorization is expensive for computers, and you can say the first number will be factorized by the first processor, second number, or any other division like this. You can go cyclic, say every other processor will handle this bunch of numbers to factorize. So you can divide the number of items you need to factorize to processors and be happy. And this might be inefficient because there might be work that you want different processors to share. And with this kind of brute force approach, you're not going to be able to take advantage of it. But it's very simple, and it's used to be called embarrassingly parallel computation if you write it this way. I think the current name is proudly parallel because people didn't like the negative connotation of it. Here's another example. Let's say you want to add a bunch of numbers, and this doesn't need to be adding. This can be any reduction. It can be multiplication. It might be finding the minimum, might be finding the maximum, as long as there are some restrictions about what it needs to be, such as associativity, but of the operation you have. But as long as those are satisfied, you can run this computation on any operation. And serially is very trivial, right? You just go over the list and sum them up. It takes order n work for a list of size n, meaning n values to add. And in parallel, you can build this thing. Usually they call it the scan operation or prefix sum operation. It's like a tree, and you can go over this data order log n times. So you will get essentially an algorithm that does n times log n computation, but it has lots of parallelism because it will just finish in log n steps, assuming you have n processors, and you can get a significant speed up out of it. So you're kind of doing a little more work, but potentially running much faster if that's what you care. Of course, again, as I said at the beginning, it needs to be associative for the parallel algorithm to be correct and match the result of the serial algorithm. Okay, so for using parallelism, there is a famous quote by Cray, which you might have heard about supercomputers. Seymour Cray was the, I think, the founder of the company back in the day, and it's been acquired by HPE, I think 5 years ago. Still makes lots of supercomputers, including the ones we use at NERSC today. And the quote is really, what would you use if you were to plow a field? 2 strong oxen or 1,000 chickens? And of course, the analogy is you would use chickens because, I mean, I guess it depends on the field and what you're trying to plow, how hard the soil is. But for a relatively easy one, you're going to cover more space. But it's really a confusing analogy. But the actual answer from any hardware expert would be that the only sustainable way to increase performance is to increase parallelism. And we go back and talk about details about why this is happening with an actual example of, let's say you want to get certain speed on a certain size data, and you'll see that there's no way within the physics laws to do that with a serial computer. But of course, there's multiple other reasons for that. So let's go over a couple of examples of parallel computers that we have today. So this is 3 broad classes of computers. On the left, you see shared memory machines. In the middle, there will be distributed memory machines. And on the right will be like single instruction, multiple data SIMD machines. Let's go dive into them. Specifically, the so-called SMPs, shared memory multiprocessors, which literally used to be symmetric multiprocessor. That's why it's SMP. And it's common that a lot of acronyms stick and start meaning something else. And we'll see it in actually the distributed memory programming lectures that some of the acronyms that are used there actually mean something completely different historically, but somehow fits the new wording. And somehow bands in music use the same kind of logic. Sometimes they change what they stand for, but the acronym still matches what they stand for now, and they just stick to it. And SMP is one example. We're just gonna call it shared memory multiprocessor to avoid confusion. So there's a single memory that is accessed by all processors, and there's potentially a bunch of distinct processors. It also includes a subclass called multi-core processors, where these so-called processors are on a single chip. But broadly speaking, they don't have to be on a single chip. You can just have, and SGI, the company, used to make these machines that had 16, 32, however many different distinct processors connected through a network to a single memory. So it can be different architectures as long as there is a one unique memory that's said SMP for our purposes. And the second class is distributed memory machines, also called high performance computing systems. And these as processors have their own memories. And there's a network that allows these processors to communicate with each other, move data, send messages. I think there's one person I need to mute. If someone has privileges to mute, okay, great, thank you. These are also called clusters because it's clusters of distinct processors. They usually actually are composed of different nodes. Each node, so-called node, can include multiple sockets of multi-core chips today. And these nodes are going to be connected to each other in some sort of cabinet. And the cabinets will be connected to each other through some sort of a higher level network. So there'll be layers of networks connecting these things, and they will scale up accordingly. And we'll see, we'll go actually particular architectures historically and in contemporary of distributed memory machines in the corresponding lecture in a couple of weeks. And finally, single processor multiple data computers really have multiple processors that perform the same operation. So the SIMD, actually, you can see that doesn't match the acronym because SIMD acronym stands for single instruction, multiple data, which I think is a little more but we're broadly defining it here. And that you can see why it's called that way, because all these little cores will do the same exact instruction on a wide data. And that wide data allows us to exploit so-called data parallels. And this actually exists in almost every single computer, including your laptop. They have these so-called AVX instructions, vector instructions, but the graphic processing units use this to an extreme, that a lot of what GPUs do is SIMD. And we're of course going to have a GPU lecture too. So I have a couple of questions and probably a slightly better quote from Bill Daly, which is the chief scientist at NVIDIA and also affiliated with Stanford still. Why is high performance computing often synonymous with parallel computing? That's the question that we're going to answer several times today. And why do we care so much about interconnect and communication? Because the last three slides just basically showed you how these processors are connected to each other in different ways. And he had this really hammering home two equalities, which I really like. He used to give these lectures about a decade and a half ago. Performance is parallelism and efficiency is locality, right? So the first equality really answers your first question in the slide, and the second equality really answers the second question here. And these are by a large extent correct today. So they haven't really aged badly. So what's not a parallel computer and what we're not going to cover in this class. So there is something called a concurrent programming, concurrent computing. Concurrency is not necessarily parallel execution, right? Your system can give you the illusion of parallelism by time sharing between threads, which is when your browser is open at the same time while you're typing in Word and listening to music. And if you have a single processor, your operating system will do all these tasks just fine, and you're not going to feel any jitters. But there's no real parallelism going on in there. So things are concurrently executing, and the processor is just simply switching from one task to the other fast enough that you don't feel it as the user. But that's not really parallelism. Concurrency can have parallelism, of course, but that's the only part we're going to focus in this course. Multiple tasks are actually active at one time for what we consider as real time, right? If you're into philosophy and whether time exists or not, that's beyond the scope of this class. And there is another thing that you might see and get confused, this thing called the distributed system. And you can think of any website such as online banking. There is usually a server. Of course, we draw it here as a single monolithic entity, but in reality, even servers are distributed to make sure that when one component fails, you still can access online banking account, or when there's high load, you can still get reasonable response times. But let's for a moment ignore that fact that there is one server and lots of clients are coming and going. There is some sort of parallelism and concurrency happening at this point, but these clients are not active at the same time. They turn active at given points, and the system is inherently distributed, which is different than what we're going to do when we say a distributed memory computer, where all these tasks are active at the same time, and everything starts together and everything ends it together. So that's really how we're going to use a parallel HPC, high performance computing computer, when we talk about distributed memory. And that's not really a distributed system in this picture sense. Okay, hopefully this clarified some of the differences between terminologies. So let's talk about some realities, which is the fastest computers, at least the ones that we know and publicly available, have been parallel for a long time, and we believe the ones that are not publicly available are also parallel, right? There's a ranking system called Top 500, has been going on for I think it started at late 80s. So you do the math, 35 years, about that much. So you can get a lot of historical data. It ranks supercomputers, at least those that are make themselves publicly known. There's lots of machines that are owned by companies and the defense industry that are probably not public but have the same equivalent computing capacity. So when you hear supercomputing today, we're really talking about parallel programming. So that's an important thing to think about. In the future, this might change. Supercomputing might become synonymous with quantum computing or some other technology that might overcome the barriers of standard von Neumann architectures. But today, when we say supercomputing, we're really talking about parallelism. And NERSC, which is up at the hill again, is what you're going to do most of your homeworks on. There's this machine Corey, which is named after the first American woman that won Nobel Prize, Gertie Teresa Corey, actually born in a now defunct empire called Austro-Hungarian Empire. So let's look at this list. But before we do that, how do we measure performance? And the real units of measure for high performance computing are generally so-called flops, floating point operations per second. And somewhat confusingly, the flops, if you don't put the /, is really talking about the number of operations. If you put the / before S, you're really talking about floating point operations per second. And of course, you talk about bytes because that matters a lot and determines how fast you can run things and how big your communication costs are, and so on. And these are for 10 to the 3, there's kilo, mega. You have probably heard about those things from your personal computers, but you might not have heard about things beyond maybe tera. So there's peta is 10 to the 15, exa is 10 to the 18, which is what we're almost about to achieve, hopefully within the next 12 months or so, meaning there will be a machine that at least projected to be, that can perform 10 to the 18 flops per second. And when we say this, we talk about double precision operations. And this goes on zeta, iota, and so on. To avoid distinction, to avoid confusion, and to address a lawsuit that came up, people actually started talking about these KIB, MIB as opposed to MB, which are like bytes are represented. And you can see that as a computer scientist, 10 to the 6 is 2020, almost, but not quite. So there's usually a distinction between those things. And the I is actually added to address the differences. And there are some quiz questions you might have to answer. Just read the notes about how you should take kilo, whether you should take it 10 to the 3, for example, or 2 to the 10. So just make sure that you read the fine print in your questions. So again, TIE 500 is really about the most powerful computers in the world, updated twice yearly in 2 big conferences. One almost always happens in Germany in June, and one almost always happens in November in the United States. And the yardstick, how we rank these things, is called the floating point operations per second, doing so-called running the LIMPAC benchmark, which is solving a system of linear equations, a dense system. So the A is a dense matrix, which is random entries, and the cost will be dominated by dense matrix multiply, if you implement it correctly, of course. One thing to note is this is not an embarrassingly or proudly parallel computation, despite dense matrix multiply achieving really good performance in modern architectures. This operation still involves a fair amount of communication. So it's not like image processing, where everybody gets their own piece of data and crunches numbers with no communication. There is a lot of communication going on in there. It's just the computation is at a higher order than communication. So it's somewhat easier than some other computations that we're going to cover today. Here's the current ranking from November 2021, which is the latest listing. So what's going on with this color coding? I tried to the colors those government machines that have NVIDIA accelerators. As far as I know, the accelerator concept became up to debate. So I'm just going to call it NVIDIA accelerators. And those are the red ones. And there's, as you can see, the majority is in certain supercomputing centers, like the Department of Energy has Oak Ridge, Livermore, and Lawrence Berkeley Lab here, Perlmutter. This machine is actually somewhat up and running, half of it, but it's not publicly accessible yet to everybody. That's why we're not doing our homeworks there yet, and hopefully next year. And there is now an actual machine from a company, NVIDIA, that they publicly acknowledge and put numbers here, which is at ranking 6. The green ones, I highlighted them green because by a certain argument, they don't have accelerators. They have their just CPUs. Some of them are CPUs that we don't use today, like the Fugaku machine or the Sunway Tyrolite machine is not the kind of Intels or AMDs you're used to today. And finally, I colored the number 10 entry because it's actually a cloud computing provider's entry here. It's Microsoft Azure as a ranking there. So one thing that is relatively surprising here is that there is no NSF machine here. National Science Foundation has no machines at the top 10. I mean, they have a lot of machines beyond top 10, but they no longer have any machine at top 10. The fastest machine in the United States is so-called Summit, which is composed of nodes that have 2 so-called sockets, which is these identical pieces of thing that are connected to a PCIe bus in between. Each one of these nodes have 2 Power 9 IBM processors and 6 NVIDIA Tesla V100 GPUs. It does actually exaops, but these are not real flops because they're not double precision, so they don't count in the race to exaflop, so to speak. The fastest machine in the world beyond the United States is Fugaku. In Japan, they have this Fujitsu CPUs and no GPUs, at least none of them doing any computation. You can see a little bit of a difference here. What Summit has achieved here is with only less than 5,000 nodes, because each node is really fat with a lot of compute power, with all these 6 NVIDIA GPUs. And Fugaku, by contrast, went to a completely different route of having, I would say, almost 2 orders of magnitude more nodes here, and no accelerators. So there's different ways of achieving the same performance. If you look at other rankings about what about the energy efficiency of these machines, it turns out actually Fugaku is better. But we're not going to cover too much about that. The Coriat nurse that you're going to be using is not even #1 in Berkeley. I used to say #1 in Berkeley, but we now have Perlmutter. It's #1 in Berkeley among the ones public can access today. And it has actually 2 so-called phases. We no longer call them phases, actually. It's just like 2 pieces of this machine. One of them has more traditional Haswell CPUs that are close to what you're used to as a multi-core processor, and the other ones have so-called KNL, nice landing processors, which have much many more cores, but less powerful cores, and you can tell it from the frequency of each core. So those are this is the machine you're going to be using for most of your homework. So one thing I said was top 500 allows us to look back in time. and see the trends of performance over the years. And these are this is really nice because it shows you not only the top ranking machine, which is this yellow line, but it also shows you the 500, the machine at the 500 rank, and the sum of all the entries in the 500. So somehow the historical trend for the fastest machine, #1 machine, is still holding today. And that is following a certain trend that's been going on since the list has started. By contrast, at around 2009, the machine at 500 rank, as well as this, actually, first the machine at 500 rank started dropping from its trend and started going into a slower slope of increasing performance. And if this continues, the processor at number 500 will be lagging by a factor of 10 from its historical trend line. Note that the y-axis is logarithmic. The change might look minimal, but it has a huge impact in actual numbers. And the sum is also started dropping from its historical trend a little later, like you can say 2015 is when this happened. So of course you can say that I can be smarter. Why are we solving the system of linear equations in one particular way? In fact, researchers, of course, look at this question as well, and they say, if we used a different way of solving AX equals B, instead of doing it with Gaussian elimination, we can just do it with a different method that solves it in lower precision and does iterative refinement after that. You can actually get a significantly higher flop rate, so-called mixed precision high performance LIMPAC and exaflop. But unfortunately, this is not allowed by benchmark rules. So that's not an accepted entry. On the other hand, you actually get the same accuracy with the original one. So algorithmic advances are not allowed with respect to this benchmark is, I think, all I wanted to say here. It's really about looking at how machines are evolving, not how algorithms are evolving. So again, looking back historically, what has happened? I did not update the slide after 2018, mostly because, again, the definition of accelerated, I think, created sufficient confusion and debate that they stopped allowing people to choose that as a distinct category. So the top 500 no longer actually allows you to draw the accelerated as a distinct entity. So this slide is going to stay as a snapshot for a while. But what you can see here is the clusters are dominating. Even the accelerated part is actually a cluster, right? It's not an x86 cluster, maybe it's an x86, but it's not getting all of its performance from the CPU. It's getting a lot of its performance from GPUs. But overall, it's an HPC system of distributed memory clusters. But that was not always the case. If you go back by a quarter century, you will see that the fastest machines actually did not involve any clusters. They had quite a lot of other machines, including symmetric multiprocessors and vector machines even before that. So what does this really tell us is back in the day, instead of building a really huge machine that's a really expensive interconnect, didn't actually work out very well, because by the time you finish building it, the CPUs were getting faster so much within that period that with the Moore's law actually in full force, that people were able to just wait it out and get a shared memory system quickly and replace it every 18 months. And that would actually be the supercomputers of that decade. How do we program these things? Back in the day when we had symmetric multiprocessors, single memory machines or vector machines, we could actually let the compiler do a lot of the work. You can write almost serial looking code and annotate it with certain pragmas and say, okay, this loop is parallelizable. It doesn't have any dependencies. Please do it so. And it would work out fine, and it will be vectorized and parallelized accordingly. Nowadays, though, almost all parallel computing is done by rethinking algorithms and software. Because of the clusters, the domination of this whole era, relying on a compiler does no longer work, and almost everybody writes their algorithms and parallelizes them by rethinking the process from scratch. I don't really know why the resolution of this thing went so bad. It actually was great when I was going over these slides before. So I just wanted to show this is really strange resolution. Hopefully you can download a version that has better resolution from the website. Let me know if that one also looks bad, and I'll find a different way of getting this source of the slide to you. So what do we see here? This is the accelerators. Remember, Intel KNL also count as an accelerator, and there's some AMD, but most of these accelerators are NVIDIA's GPUs. And this number that they reach is 150-ish. And from the bad resolution, you're not probably seeing that. What that really says, just a little under 1/3 of all systems have accelerators and co-processors today. And this is just the system count. The y-axis, the number of systems. The actual performance share is significantly higher. So that's the trend. What about the chip technology? How is it evolving? At least nowadays, we're seeing some real competition re-emerging here. In the last decade or so, we have seen Intel's share getting bigger and bigger, almost to 95% plus of machines on the CPU end. Again, this doesn't include the GPUs here. Where Intel CPUs, nowadays we see the AMD getting back up in this game, and there's actually quite a bit of ARM-based processors that you can run your computations on cloud instances that are not reported in top 500. And one example is Amazon's so-called Graviton processors. If you haven't heard about it, you can just Google that. They're at their 3rd generation today. What other changes happening? As we said that back a century ago, you would just wait it out. Instead of building a massive machine, you would just replace it very frequently with the CPU generations getting faster twice as much every 18 months. Nowadays, that's not happening, and the cost of replacing a machine is really prohibitive for a lot of the supercomputing centers. So the replacement time has increased significantly, and average system age is really high up compared to its historical trend. And the other reason, of course, is the CPUs are not getting as faster at the same rate that they used to. So the incremental value of upgrading your system is lower. So there's the cost and there's the value. So I talked a lot about top 500 of ranking processes, but there's another way of ranking things, which is the actual real application performance. And Golden Bell, one of the pioneers of HPC, back in the day said, if you can show me real speed ups on a real application, I'm going to give you, I don't know if it was always this much, this amount of dollars. I don't know the historical number, what it used to be. And that became the so-called Golden Bell Award that's been handed out at the SC conference every year. And its scope has been broadened to include not just raw performance on real applications, but generally innovations in applying high-performance computing to science, engineering, and data analytics problems. And this is, you see a picture of 2 teams sharing the award 2018. One of the teams is actually stationed here at Lawrence Berkeley National Laboratory. The people on the right are mostly from there. It's actually not true. They're all over the place. This picture, people just This is two distinct teams, one led by Oak Ridge, one led by Prabhat here. Kathy Yellick did this plot, which compares the performance of the Golden Bell winners to the top 500 fastest machine. And on the y-axis, you see the flops, floating point operations per second, with the nice forward ampersand. You see that surprisingly, I mean, maybe counterintuitively, the trend is holding. Maybe that's just the bias of the Golden Bell Award Committee to choose things that perform very well, or maybe that people actually are able to take advantage of these supercomputers as much as the top 500 high performance LIMPAC benchmark does. You'll see that there's almost a strong correlation between these two numbers. What you might find slightly strange is that at certain years, the Golden Bell winners operation performance rate is higher than top 500. So we know top 500 is a relatively easy problem, solving a dense system of equations. But we also know that it's not an embarrassingly parallel problem. So it's not a super hard application, but it's not trivial either. But the real reason why this can be so much higher, remember this is y-axis is log scale, is that there are different ways of computing flops. The top 500 only reports the double precision rate, and some of these entries actually don't use double precision. In particular, this number is from the teams that I showed in the previous slide. Both of those are using reduced precision operations, like 8-bit, 16-bit, 4-bit, depending on the application. And we call them AI ops or AI flops. No pun intended here, because they can get away with reduced precision arithmetic and still get the same result. So we're going to go a little bit about science examples using HPC. You might have seen this picture. What used to be 3 pillars of science were theory, experiment, and simulation. Obviously, before that, there was 2 pillars of science. There were theory and experimentation. And the simulation became the first commonly accepted 3rd pillar of science. What simulation really means that we put the known mathematical laws into a computer program and let the so-called computer model of whatever we're trying to simulate, whatever phenomena we're trying to simulate, evolve over time. And that's really called simulating. And why would we do that? Sometimes we want to look at things that are too big to observe, or too small to observe, happening too fast for us to capture, or happening too slow. We can't really wait for it. And it might be too dangerous. And these are very different examples. For example, the universe, we can't really wait it out. We can't go back in time either. Climate change, we have to do forward simulations. We can't wait until post-apocalypse comes. And jet engines, we can't always do the experimentation safely. We have to simulate a lot of these things. Airplanes, before they get certified, they have to do a lot of simulations about what can go wrong, and so on. I'm hoping this resolution will be good, but this just shows a simulation of what would happen to the globe if the climate warms up by a couple of degrees. And here you can see certain hurricanes are forming. And the way this is mapped to a supercomputer is you divide up your globe into certain shapes. I mean, there's obviously preferred methods over the others. Scientists have studied the right ways of discretizing globe. They do it in hexagons and so on. And each processor will get a piece of it to simulate. This sounds like too easy, and it's not in practice, because obviously some event happening at location A will affect location B as that weather moves throughout the globe. So there has to be a lot of communication between processors. So you can't just simulate your own little piece of globe independently from other processors. And so why do we need faster computers, right? So let's play this again. So you see two different pictures here, a simulation of the same phenomena on different generations of supercomputers. And that's kind of why the resolution is different. On the top, you see the resolution so-called 200 kilometers. And at the bottom is 25 kilometers. So it's 8 times better. Is that true? Mm-hmm. I guess so, 8 times better resolution at the bottom. And that's enabled by the more powerful supercomputers. It's not just, it's visually more interesting, right? The bottom one is visually more interesting. You can see a lot of different things that you can't see at the top. At top, things kind of are smoothed out due to lack of resolution, but you're actually learning more at the bottom. You don't see the formation of hurricanes and extreme weather events at the 200 kilometer resolution, but you can see them at the bottom picture. So it's not really just visual effects. High performance computing is used, and simulation in particular, used a lot in industry as well. And a lot of the same technology that's been developed over the years are actually usable in this space as well. So it's just one example. This code was developed, called Chambo, was developed for subsurface modeling of Earth. And it turned out that you can apply this thing to something called pulping in paper manufacturing. So paper manufacturing is very energy hungry, and the majority of the energy is wasted in this process of cooking wood chips to open up the fibers, the so-called pulping, to create the paper materials. And I don't know if there is a, yeah, there is a simulation here. Good. So you can see how the same code can be used for this purpose versus subsurface, Earth subsurface modeling, right? And both of these applications used technology called adaptive mesh refinement, the so-called AMR, and we're going to cover some of the principles of AMR in the later lectures. Hopefully this is done. Here's a different kind of application. So far, what we talked about was really large-scale simulations. One huge simulation or a bunch of simulations, such as the one that we did with climate modeling, where we had like, okay, let's simulate 10 different scenarios, but each simulation was really large. But by contrast here, this materials project started with a high throughput use of high performance computing. So you would get different materials with different properties, and you would do massive amounts of simulations, one per material, and try to predict try to simulate the properties of the material. Over the years, the project has evolved to use more and more machine learning, especially for guiding the search space of discovering new materials with certain desired properties. But it really started as a high throughput, high performance computing project. And finally, no, not finally, I have a couple more simulation examples. You can use high performance computing and simulations to figure out how to capture carbon instead of releasing it back to the atmosphere, how to capture it, and to avoid climate, warming of the earth or climate change, whatever is the politically correct word to use. And of course, it's been used to simulate materials that can be used as drugs for COVID-19. You'll see lots of papers published on this space, which ones will bind better to the spike protein. And you can just simulate all known compounds that are used and accepted as drugs by FDA, and see if any of these things actually would be useful for this, right? And that's been done. And many other things are done too. So I'm going to stop giving examples of more and more simulation applications here. But let's just say that a lot of these simulation projects are now part of this big umbrella project within Department of Energy, the so-called exascale computing project. And we do a lot of those, we take part in a lot of those within the Berkeley lab itself, the so-called Lawrence Berkeley National Laboratory. In this picture, The last two ones are not simulation projects, the genomics and photon science. And we're going to talk a little bit about the genomics case in the high performance data analytics part in a couple of minutes. Okay, so we covered simulation and how high performance computing can be used in that. The fourth so-called paradigm of science, and this I believe is also sufficiently commonly accepted, is data analysis. Remember the big data craze of a decade ago. And remember, we're not actually analyzing experimental and observational data. We're also potentially analyzing output of simulations. Sometimes we just run a large simulation and that just creates terabytes and petabytes of data, and which we have to then analyze. So there's two kinds of data that we can analyze: observational and experimental data, as well as the output of simulations. And symmetrically to the simulation cases, this is also used for data sets that are too big, too complex, too fast, meaning the data is moving too fast before we can capture. Happens a lot with particle detectors and used in particle physics, too noisy or too heterogeneous. And a couple of these examples are shown here. You can argue that it's not just like one, right? So you can say the genomes from sequences are too big, but you can also say they're too noisy as well. So more than one attribute applies to each one of these problems. So there's two highlights of this slide that I want to go over. One is that it seems like our compute performance increases, at least on a single processor, is not keeping up with the growth of certain data sets. The detector output from particle physics is this red line. The sequencer output that is for genome sequencers is the orange line, and both of which are growing faster than the processor speed, and worse from the memory performance. And so what that really means that in order to be able to analyze data sets that are coming from these data sources like detectors and sequencers, we have to do more than just mapping them to computers efficiently. We have to take advantage of parallelism as well as potentially more clever algorithms. And the other parenthesis side note, which is a conclusion of this picture, is this gap between processor and memory that's been opening up is why we care about data movement, because the cost of accessing data is relatively increasing relative to the processor speed. And we're going to, of course, Jim will cover a lot about communication avoiding algorithms as part of the sources of parallelism lectures. And we're going to come back to that theme over and over again throughout the semester. So this project that high performance data analytics, or HPDA in short for genomics, was led by Kathy Ellick, which was one of the instructors, as I said, before she became the vice chancellor for research. And here's it's really not a single genome, but so-called metagenome, which is this group of organisms that kind of live together on bacteria, viruses, archaea, and fungi that you would get, and they have their own dynamics. And you can look at things like what happens to those dynamics after a wildlife, and how do microbes affect disease and growth of certain plants that we care about for bioenergy, and so on. And lots of clever algorithms are developed and are running on large-scale computers, including the Summit, which is the #1 machine that we have at US, and of course, all the machines that we have at NERSC. And this, how do I say this? These data sets are massive for the kind of computation that they run. Each one of them are larger than a terabyte, up to 10 terabytes of data. And another application of high performance computing to genomics was actually from that picture that won the Golden Bell Award in 2018, where they looked at combinations of genes that do certain tasks. And this is really a giant so-called GWAS study, genome-wide association study, what combinations of genes create what phenotype. And they basically brute force looked at all three-way combinations, I think. And they were able to use reduced precision arithmetic on the GPUs on Summit and achieved over 2 exaops per second on the Summit computer. Again, thanks to using lower precision, they were able to break the exascale barrier because the machine is not actually capable of doing double precision exaflops. Is there a fifth paradigm of science, or are we done yet? Well, there's an argument that the fifth paradigm of science is machine learning. And this is not as commonly accepted yet. You can argue that machine learning fits within data analysis, but you can argue that machine learning fits in simulation too. So it's somewhere in between, and we're just going to talk about it without arguing strongly either way. But the actual problem from the perspective of computing is that this figure that is from OpenAI shows that the computing need of different deep learning models over the years, starting from AlexNet in 2012, I think. And it ends in 2019. I believe the trend is still continuing. And over those 9 years, the compute need of these models have increased by a whopping 300,000x. To compare that with what the fastest machine in top 500 did, its performance only increased by less than 10x. So that's, what does it say? It means in order to be able to keep up with the increased computational demands of deep learning and in general machine learning, we might be building more and more powerful computers in the future. So this is a source slide from Prabhat, which used to lead the data analytics group at Berkeley Lab. Now he's at Microsoft Azure, running their cloud services, leading their efforts at the HPC for cloud, so-called. But this just shows you the analogy between what the industry and the science do with the similar technologies, right? This the classifying pictures and objects in the pictures involve obviously localizing, object detection, segmentation, and classification. And you can directly apply the same ideas to classify extreme weather events, whether they're hurricanes or atmospheric rivers. You can say there's localization, there's object detection, segmentation, and classification, right? So there's quite a lot of technology transfer that's possible across domains. Obviously, scale is very different. Looking at this data, that's this climate simulation. It's a huge data compared to a picture. But machine learning is actually successful in playing well with the simulations in general. So this is, again, from the same 2018 award. I keep going back to the same Golden Bell Award because there are two different teams, so I can talk about different parts of it. They use deep learning to predict extreme weather events. And there's the ground truth that they can measure their success against. And it turned out that the deep learning results were better, meaning smoother than the heuristically made labels that they used to use before the deep learning solution. And this achieved over again an exaop performance on the same machine, the Oak Ridge Summit machine. And here, what we see is, let me see if there's an animation here. There doesn't seem to be an animation. People using machine learning for generating scientific data. So generally, as I said, people use simulations to generate scientific data, but you can use certain kinds of machine learning methods, such as, in this case, generative adversarial networks, to build convergence maps of gravitational lensing And the important thing, it doesn't matter what the actual application is, the output of these GAN-based method was physically realistic, meaning it was statistically indistinguishable from the output coming from the detailed simulations. And why would we then do that? Potentially, GANs can be made more accurate or can be made faster. So they have the potential to replace some of the simulations we do. Okay, so that's enough for pillars of science. Now we're going to go back to parallel computing and classifying different applications and by their kernels, by the kind of computations they do. You might actually feel like overwhelmed at this point. So let me see if there are unanswered questions so far. I'm seeing that the website one looks bad. Okay, I'll send you the I'll send the whole class the high resolution pictures for those low resolution versions. Okay, looks like our things are self-answered. Thanks very much. You might feel overwhelmed at this point because there's all these complicated applications running on these complicated hardware. How do you even go about getting good performance out of this thing? And how do you keep coming back to a new application, figuring out how to run it on a supercomputer? It seems like a daunting task, and it really is. But there's things that help us, which is we can look at a big class of applications and figure out what is common across them. And that's really important, because otherwise you'll have to start from scratch for every single application and try to rewrite everything and learn the same things that your colleagues already learned about how to map that class of applications to supercomputers. So this started with Phil Colella, which I think Professor Emeritus now, used to be at the lab. He also retired from the laboratory as well. He gave this talk, never published about it. He talked about the 7 dwarfs of scientific computing in a DARPA presentation. He actually was talking about simulation only at the time. Remember, this is almost 2 decades ago. And he identified 7 things: dense, sparse linear algebra, particle methods, structured and unstructured grids, spectral methods, and Monte Carlo simulations. And we're going to cover everything except Monte Carlo, I believe, in this class. And we no longer use the word dwarfs for various political reasons. But that was the historical thing. If you need to look for that presentation, you will have to write the exact code in there under the dwarf picture. So one of the large projects within EX department, led by, I believe, Dave Patterson was the director. David Patterson is PARLAB, Parallel Computing Laboratory. And the goal of PARLAB was really to tackle the multi-core parallelism that was prevalent and was daunting for the industry, a lot of people in mid-2000s. And within that, Jim Demmel, which is my co-instructor, is actually part of this laboratory. And I came to Berkeley, at the Lawrence Berkeley lab, right towards the end of this project. And they looked at a wider class of applications. And these are not necessarily large-scale distributed memory parallelism. These are the kind of things that you would run every day in your laptop, multi-core processors. So it includes a lot of things like playing music or browsing and so on, not just the large-scale parallel simulations. And they identified so-called motifs of 13 of them. And the color density, or not the density, warmness of the color identifies how important it is for a particular application, which basically means take sparse matrices. They're mildly important for, let's say, the spec benchmark or very important for machine learning, not at all important perhaps for browsers and so on. Later, National Academy's report, which actually some of the faculty in Berkeley, including Michael Mahoney at the statistics department, have contributed to this, classified 7 giants of data. They wanted to call this giants. I suppose because the title of the report talked about massive data analysis, so calling these things dwarfs or motifs wasn't enough. It had to be called giants. And they identified 7 again. Maybe they just wanted to stay symmetric with the Phil Colella's dwarfs. And we're going to see that some of these things like generalized embody and alignment actually comes up a lot in computational biology. Overall, it's commonly accepted that these are a good place to start for looking at the basic computational kernels to do data analysis. Just as 7 dwarfs of simulation was actually commonly accepted, with a few exceptions, as the really important kernels that you should optimize on a new machine. And another study that I contributed and led by Kathy Ellick, we looked at motifs of genomic data analysis, meaning you have large genome data, and we broadly define genomes to include a lot of things like transcriptomes, which is the RNA, proteins, and metagenomes, which is these clusters of genomes we talked about that live together, and identified some of the commonly happening things, which is dense, sparse, alignment, generalized embody, and graphs. You'll see that 5 of these at the bottom is common with what we have on the 7 giants of data, except that the sorting and hash tables was not covered by either simulation or the 7 giants of data from the National Academy's report. So that's the new stuff that's going on here. And okay, we're in a good place now. So the old version of the slide said why the fastest computers are parallel. And we already talked about this. Remember the Bill Daly quote, that's necessarily parallelism is the only way to get performance in a sustainable way. But we have a new version of this slide, which is why all computers are parallel computers, including your cell phone and your laptop, and potentially even your car that is running all this car plays and so on, and detecting the objects that are coming and braking before or alerting you to brake and so on. So let's talk about some well-known law called the Moore's law. And Moore's law really talks about transistor density. The transistor density increases the way Gordon Moore has stated, who is the co-founder of Intel, that the transistor density would double roughly every 18 months. First, this trend, held for a long time. Again, there's no law here. This is not a physical law. This is a statement about observations or prediction of the future. And so it's kind of incorrect to call it law, but it holds for a long time, held for a long time. And then it slowed first. And first it became every 2 years. And then it started falling off from there. But you can see that for a good while, things worked out just fine. And 2 different things have happened, actually. Not only the transistor density doubled at the rate Gordon Moore has predicted, but also the frequency, the clock frequency of CPUs also increased in a particular trend that followed the predictions. Not necessarily the same slope, but the slope somewhat stayed constant throughout the decades. So, okay, more recent data suggests this is no longer going to happen. But let's talk about a couple of other things. What happens when you try to shrink transistors by a certain size? Well, when you look at a transistor in one dimension of it, you shrink by a factor of X. The clock rate goes up by X because the wires become shorter. I mean, there's some issues about power leakage, and that's the reason why this no longer holds. But that the leakage was small enough in the past that it was pretty close to X. And because the area is square of one dimension, the transistor per unit area goes up by X squared. And usually the chips got bigger, the die size increased. That used to be approximately X2. Again, a lot of things are back of the envelope in the slide, which is how people actually run this business. So potentially the raw computing power could go up by X to the 4. Again, area goes up X squared, clock rate goes up by X, die size increases X, you put all of them together, X to the 4, and usually X cube of it was devoted to more caches or extracting more parallelism using instruction level parallelism. So you got like X times faster overall. But what's the limit of this thing? How much you can push this idea? If you can, again, this is a bit of a overgeneralized example. Let's say you want to build a teraflop machine using 1 byte of data, and you want this machine to be a sequential machine. You don't want it to use any parallelism. And you have to assume that you're going to actually make good use of this data. So you can't just get two floating point values and keep multiplying them, until infinity. That would actually run very well. But let's assume you're doing actually a good computation, important computation that accesses this 1 terabyte of data. So you have to go back and forth and get data from the memory to the processor. Well, if you do the mathematics, you'll see that you have to kind of fit this data within the 0.3 millimeters of the processor, because any farther, then you can't get it fast enough to sustain the 1 terabytes per second rate. So the data needs to live really within a certain area close to the processor, so that your processor is not starving for data. And if you do the math beyond that, how do you put 1 terabyte of storage in that area so close to the processor? Well, that means each bit will have to occupy 1 square angstrom, which is the size of a small atom. That looks already fairly impossible. But even if it did happen, that would be your limit. So you have basically no choice but to increase parallelism to get more performance. So that's really one way to look at why you need parallelism. There's other issues, which is heat, right? So, very famous figure from about, I think this is 15 years ago. What people have figured out is if they did business as usual and tried to increase frequencies as they did in late 90s, they would reach the power leakage, basically power density of the sun's surface eventually. So that's why I was an undergrad when I got a 3 gigahertz machine, and it's been a long time. I still get, I don't even get 3 gigahertz machines anymore, right? They kind of toned it down a little bit so that they can pack more cores. But really, it's about leakage. When the transistors go so small, then a lot of the power actually dissipates, and that becomes unsustainable. So you could, the dynamic power is proportional to the square of voltage and frequency times the capacitance. The solution people have found, instead of increasing frequencies, they can still increase transistor density, but instead of increasing frequency, they're just going to add more parallelism and put more and more cores. And this is not just for power. Of course, that was the real issue, the power wall, so-called. The other benefit of this is the serial processors were wasting a lot of energy. In order to extract a lot of performance, they were doing lots of speculative execution. and wasting a lot of energy doing computations that actually never materialized. So we still have more transistors. In some sense, Moore's law, by definition of transistor density, is not dead yet. It is just morphed into something different. Instead of getting higher clock frequencies and faster serial processors, which was usually an illusion anyway, you get more cores. What is dead is this so-called Dennard scaling, which is the transistor dimensions were going down by a certain factor, and that was reducing the area quadratically. This had this really virtuous cycle that eventually the power consumption were decreasing by 50%, and you can read about Dennard scaling if you care too much. But because of leakage, it's no longer working out. The other yield for parallelism is chip manufacturers figured out that there's a lot of defects, and they had to throw away a lot of processors that they built. So if they have a lot of cores in a single processor, they can build it with the optimum goal that they'll be, like, they can say to the manufacturers, give us 76 cores. And if up to 8 of them are bad, it doesn't matter, because they're advertising to the customer that there are only 68 functional cores. So that allows them a lot of margin, and they get good yield for that. So sometimes when you buy a chip, it is possible that there are there is more functional chips in there. It's just not on because it just by chance was manufactured correctly. The company wasn't hoping them to be functional. That's one way to improve your yield. So we already talked about this. The Dennard scaling is dead, so because of power issues, and the expectation is Moore's law, the transistor density will follow it. But the takeaway for our course is that there will be a growing burden on software to deliver better performance by extracting more parallels. So finally, we get this reinterpreted Moore's law. The number of cores per chip can double every 2 years. It might not happen, but it can. Clock speeds will not increase. It might only decrease because putting more chips might have your full processor go out of the power budget very quickly, and in which case the chip manufacturers might opt to actually decrease your clock speed. There'll be lots of concurrent threads, and you have to deal with inter-chip and intra-chip parallels. And there's actually a slightly different way of looking at it these days that are, if you buy a new Mac laptop, you probably have an M1 processor, which is actually a heterogeneous machine with different kinds of CPUs in there and different kinds of GPUs in there. So it's not just homogeneous parallelism either anymore. Well, I don't think it ended. It's still there. So I'm going to update the slides maybe after this. But overall, parallelism is everywhere. Every single machine you can get your hands on is some sort of parallelism. These pictures are actually somewhat homogeneous cores, but a lot of things that started from mobile, like your cell phone or iPad, that already had heterogeneous chips, and now it's moving into the bigger products like laptops with the M1 that I just mentioned. So there'll be a lot of parallelism. People will take advantage of them. There is a caveat though. We have to kind of talk about this thing called the Amdahl's law. If you have a big computation with lots of stages and you choose to parallelize only a fraction of it, no, it doesn't matter how big the fraction is. As long as you don't parallelize all of it, which it says that your speed up will not be linear, no matter how good of a job you do algorithmically and implementation-wise. Even if your components of the ones that you parallelize are independent of each other and they don't communicate at all, if you miss a fraction, that will come back. And that fraction, let's say it's 10%. What does that mean? You put that number in there, says your speed up will be limited to 1/10%, which is basically 10, right? So you're trying to make this S go to 0 so that you can get as much speed up as possible. Okay, I'm gonna go forward, and instead of talking more about Moore's law, I'm gonna talk a little bit about course logistics. This is our new website, and almost everything you need is in the website, including this email address. Instead of emailing each instructor independently, which people can miss that email depending on where they are that day. You should email us at this address, which is also on the class website. This goes to every 6 of us, which brings me to the course staff. I'm hoping the majority of the course staff is here. So I'm Aydin Buluc. I'm at the EX department and at the Lawrence Berkeley National Laboratory. And my co-instructor, Jim. I will hopefully have people on video and introduce themselves, at least the people who are online.
So, hello, look forward to teaching the next lecture on Thursday.
Yes, that's right. The course schedule is also online. There might be some minor changes on dates on some of the lectures, but overall, it should be stable for the next couple of weeks. If the GSIs are here, can they introduce themselves as well briefly with the order that's in the slide?
Hello, I'm Vivek. I'm a GSI and a second-year PhD student here.
Hello, everyone. I'm Demmel. I'm a third-year PhD student working on distributed machine learning.
Any other GSIs online? Okay, well, it's okay because we didn't actually have everybody signed up. There's usually going to be at least one GSI that's signed up to be online throughout the course, and that will help answer some of your questions when the instructor is busy giving the lecture. As for instructors, we try to attend each other's lectures except for travel or vacation days and so on. That should also help answer some of the questions. There might be some unavoidable conflicts, but overall, we strive to actually attend lectures. And we have an excellent GSI team, 4 people. This is should be enough for this number of students so far enrolled. So this is the statistics of the officially enrolled students that I just drew yesterday. So it excludes all the undergrads. We're still awaiting class expansion, sorry, and for the reasons I gave right before I started the lectures, it's really the staff is overwhelmed at the beginning of the semester. And this is not like a elastic Amazon cloud that you can just hire, spawn off 10 other clusters when the demand increases and turn them off when the demand decreases. Right? This is actual human labor. So let's give it a couple of more days. And if it doesn't happen, we might not be able to expand the class because the homework one will be out on Thursday and people will start forming teams. So that kind of puts us a kind of a strict deadline. What do we see here among the grad students? We have a lot of PhDs and masters. I tried to subdivide the particular masters things to get higher resolution here. We see a huge crowd of computer science and EX in general students. On the left plot, this is somewhat higher than its historical trend, and it's mostly due to the Masters of Engineering students. That is the 44% of Masters of Engineering students. I would say almost all of them are EX students, so that's why it creates a big chunk of it. But we do have quite a bit of interesting majors there as well, and you can see that lots of these little pieces of the pie, for resolution reasons, they were not drawn.
There are 18 different departments in total.
Oh, Jim did this math, great.
Yes.
A version of this class is also broadcasted through an NSF project to many other universities over the years. I don't know what subset of them are taking this year, but this is somewhat of a union of different universities that took a version of this class. Mostly they follow the lectures that have been captured last year so that they can go out of sync from us safely. And we're going to talk about the different programming languages and different paradigms of programming. Distributed memory machines, data parallel, shared memory. We'll use these languages. We'll cover a lot of performance models and hierarchical algorithms, communication avoidance, lots of important laws in parallelism, like the ones that I talked about, Amdahl's laws and Moore's law, but also equally important Little's law, lots of applications in machine learning, biology, and cosmology, and some techniques for motifs in scientific computing and data that we're going to cover in distinct lectures. You can see, as I said, the full schedule on the class website. Just for record, repeat it here once more. We will have quizzes. That's important. Every lecture, a couple hours after each lecture, we're going to release quizzes, and you'll have time until the beginning of the next lecture to take that quiz. It's usually just 5 questions. So you just need to be aware of the contents of the lectures. And these will constitute a percentage of your grade as listed on the class website. I should update this. Labs will use Wednesday slot for optional labs and 1 per homework. It will be updated. We will assign you groups for homework 1. And sometimes these groups persist throughout the semester and be reused for subsequent homeworks, but you don't have to. Only for homework 1, we're going to assign you groups. If you're not in Piazza, I added everybody who was either on a wait list or officially signed up last week, but I'm not going to go back and add more people from these lists. The way to sign up is just clicking on this and join as a student. Anybody with a Berkeley EDU address can actually join as a student to Piazza. And finally, look for an email from us tomorrow morning to sign up for an account at NERSC. This is the platform you're going to use for your first homework. The reason we're waiting is because NERSC is going through its annual transition, which means they don't actually accept new users until 8 a.m. tomorrow. So thank you very much, and looking forward to a great semester together.